Hey there. Let's build a binary search tree together. If you've seen my previous videos, you understand now how to define a binary search tree, meaning what are the rules that you have to adhere to if you want your thing to be a binary search tree. Also terminology were in previous videos. So in this video, we're just going to take a bunch of random numbers and we're just going to start dropping them into our tree and see how the tree builds itself out. We have to build our tree in a specific way if it's going to be valid. We're not going to rearrange our tree and try to make it super pretty. This is going to be like a real binary search tree. It might not be pretty, but it'll be real. Let's see if I can find those numbers that I was going to set up. Okay. So for this particular video, I think I'm going to do two videos. I want to build a binary search tree using the following numbers. They're not special. They're going to produce a tree that is okay, not perfect. But what I mean to say when I say inserting these numbers is one by one, we'll look at each number and we'll drop it in the tree and we'll see where it falls according to binary search tree rules of insertion. Then we'll just go to the next number and then the next and the next. When we're done, we should have a tree. And if you follow along at home and you use the right rules to build your tree, then if we use the same sequence of numbers to build the tree, we should end up with identical trees. They won't suddenly be different. They're deterministic. Okay, so the first thing that we should try to understand is when we want to insert a node, this 73 node right here, the first thing we should ask ourselves is, do we actually have a root node for our binary search tree yet? Right now, the answer is no. This is just a blank tree. There's nothing in it, which means that first number is going to be the root node. You might be tempted to say, nah, that's a sucky root node. Let's do something else. Well, I don't know. I mean, you just have to let the numbers fall where they're going to fall. Just because a number seems to suck as a root node doesn't mean it's not going to be the root node. If it's the first thing you added, it's going to be the root node. Don't try to change it, or you're going to end up with topology that doesn't match whatever system or person is trying to grade your work or evaluate your work. So we have no root node. That means the 73 is just going to be the root node of the entire tree. We're now done with 73. I'm going to duplicate this slide real fast. And we'll say now it's time to try to add the 98. You know what? I think I can do better than that arrow. I can make a nice, cute arrow with this program. I'm going to do this. Can I yeah. Hang on, one more try. Nice, okay. So now let's add the 98 node. The first thing we have to ask is, do we have a root node? Yeah, so we can't actually put the 98 there. We now have to make a decision. If you recall in my previous videos, the lesser values go on the left and the greater values go on the right. In these trees, which we're not going to support duplicate values with. If you wanted to support duplicate values, you could do something like less than or equal to would be on the left and greater than on the right. There's a bunch of other ways you can do it, but I'm just going to say no duplicate values in our trees. So we look at the 73 node and we ask, is that where our 98 is going to go? It can't go there because 73 exists. Now we have to ask the question, does 98 belong on the left side or the right side of the 73? Well, because 98 is greater than 73, it belongs on the right side, which means I'm going to duplicate this node over here, and I'm going to try to draw this well, which means basically splitting the difference in terms of the empty space and trying to keep the same rank as we go down one level of descendancy, or like one generation down at a time. So the next time I go down a level, let's say I do a left child in the future, it should be at the same level as the new node I just added. So I did a duplicate and I forgot to change the number. And then I'm going to do a line to connect the 73 and the 98. So now the 73 has a right child, which is 98. The 98 has a parent, which is 73. And we're done adding the 98. We have to just move on to the next number. Okay, so I'm going to move on to the 12. Again, we look at the root node, it's occupied. We cannot put the 12 right there on the 73. We have to make a decision. Do we go to the left or the right of the 73? 12 is less than 73, so it belongs on the left side. So that means our decision now is to jump to the left side. Notice how the left side, there's no child on the left. That means that's where the new node is going to go. So I'm just going to select this, duplicate it real fast, maybe stick it on the same vertical coordinate, and then also try to split the difference on the screen just to make it look pretty. I'm going to update that 98 so that it is now the 12. I'm going to add the line that connects the 73 with its new left child 12. And then we're done adding the 12. Okay, no problem so far. We then are ready to try to add the 45. Maybe I should squish this a little bit. Nope, that looks gross. No, it's okay. We'll do that. We're going to add the 45. Again, we look at the root node. It already exists, so we can't put the 45 there. Instead, we will just kind of decide, does the 45 belong on the left or the right of the 73? Okay, well, belongs on the left because it's less than 73, so that means I'm now going to make a little decision. I'm going to jump down to the left. If you're in some code, you're following the left child pointer down. But notice how the left child pointer, or the left child, it already exists, so we can't actually put 45 right there. We have to make another decision. Does 45 belong on the left or the right of the 12? Well, it's greater than 12, so it belongs on the right side of 12. So I'm going to highlight this and duplicate it. I guess I'll just do it that way. Then I'm going to update that number with 45, and then I'm going to connect the 12 and the 45 with a line. So now 45 is the right child of 12, and 12 is the parent of 45. It's at this point that a lot of people start to get frustrated with me, and they say, well, how come the 12 is like all the way to the left and the 45 is like, didn't become like, you know, a level higher, because it kind of seems like it's closer to 73. Shouldn't the 12 be hanging off the left child of the 45? No. Don't rearrange the nodes as you're building the tree. Just let the nodes fall wherever they're supposed to go. Another tip is if you're building a tree that has other data types as the T types inside of the nodes, as the template types inside of the nodes. For example, right now I'm just using integers, right? The T type is int, at least in my mind. If you wanted to put dinosaur objects in the tree, all you'd have to do is make sure that your code for your dinosaur class, for your dinosaur object, had its inequality operators implemented, you know, less than, greater than, and then the tree would still know where to put all the objects. So you could make any kind of custom object you want, and they would all fall in their correct places in the tree as long as the operators actually worked. Just as a side note. Okay, so now we're ready to add the next item. So I'm going to erase this stuff here, and I'm going to move the arrow from the 45 to the 67. So now we're going to try to add the 67. We look at the root node, it's occupied. We should go to the left because 67 is less than 73. We look at the 12, that's occupied, so we go left or right. We should go to the right because 67 is greater than 12. So we look at the 45. Again, it's occupied. There's a node there, so we have to make another decision. Do we go to the left or to the right? Well, 67 is greater than 45, so it goes on the right side. So I'm going to duplicate this off to the right side and down a rank, and we'll call that the right child of 45. Let me update the number here to 67, and I'll connect that as the right child. Okay. And now we're done adding 67. Any questions? I'm just kidding. That was rude. Just know that my heart is with you if you're asking questions. Send me a comment in the comments. So now I'm going to move over to the 10 here. Again, we look at the 67, the 10 belongs on the left, so we kind of go to the left. We look at the 12. The 10 belongs on the left of the 12 because it's less than 12, so that is an available slot, that's an available child pointer, so I'm going to say the 10 is going to be the left child of the 12 node. Maybe I'll stick it all the way over there. Let's see, is there anything less than 10 in there? Nope. Okay, so we'll be good. We have enough space on the screen. So change that to a 10, do the connecting line. So the 10 is now the left child, the left child of the 12 node. And now we're ready to add the next node. Okay. So now the 43 is the next one we want to add. One more time, we look at the 73 node. The root node is occupied, so we have to go to the left because 43 is less. So, oops, that's a line. So now we look at the 12 node. Is 43 greater than or less than the 12? It's greater than, so that means we go down to the right. But the 45 is there, so we have to make another decision. 43 is less than 45, so we go to the left. That means this 43 is going to be the left child of 45. And again, don't try to make the tree pretty or better just let the nodes fall wherever they're supposed to fall, according to the rules of less than or greater than. So now we got the, whoops, I forgot to change that to a 43. The 43 right there, and we are now ready to add another node. So I'm going to like erase this stuff here, and I'm going to move the arrow to the 11. Now, once again, we're looking for the root node. It's already occupied. We say that 11 is supposed to go on the left because it's less than. We look at the 12. It's occupied, so we have to go to the left because 11 is less than 12. We go to the 10. And that's also occupied, so we have to make another decision. Is 11 greater than or less than 10? It's greater than, so that's why the 11 goes on the right side of the 10. So I'm going to duplicate this over here. Notice how I'm trying to keep same ranked children or same depth children physically at the same level. It's a lot easier to debug your diagrams if you do things this way. Notice also, as I mentioned in a previous video, that every left descendant of a node should be physically on the left side in my diagram, and every right descendant should be physically on the right side. That just makes the diagram way easier to debug. What do I mean by this? Look at 73's left descendants, its left subtree. They're all physically on the left. Look at the 12 node, all of its right descendants or its right subtree. They're all physically on the right. So if you follow that rule, it's just way easier to debug. I think I forgot to update that number from 43 to 11, so I'm going to do that now. And we are ready to add the next number, the 99. So I'm going to do this. We're looking at 99. So first we start off by looking at the root node. It's 73, occupied. 99 belongs on the right side. So now we bounce to the right side and we look at the 98. Whoops, whoops, whoops. We look at the 98. That's occupied, so we make another decision. The 99 belongs on the right side of 98. That slot is available, so now we can say that the 99 node is supposed to be a right child of 99. Sorry. The 99 is the right child of the 98 node. I'm getting a little confused. Okay, so I'm going to do a little connecting line there. And we're ready to add the final value into our tree. So I'm going to do, let's see. Oh, I accidentally erased the arrow. Oh, there it is. We can add the 32 next. And if we look at the 73, it's occupied. 32 belongs on the left. So then we just kind of like follow down to the left here. We look at the 12. 32 belongs on the right of 12. So we follow down to the right. 32 belongs on the left of 45. So we follow down to the left. 32 belongs on the left of 43. And so we will make 32 the left child of the 43 node. So I'm going to like select this real fast. We go down a full rank, and I'm going to try to split the difference between 12 and 43 here, just to make the diagram easier to debug. Okay, so then I'm going to do, it's looking a little gross, but at least we're finished. I have to update that 11 to be the 32, and now we're done building our tree. Okay, so some things to point out real fast. Notice how the tree is lopsided, and if you look at various parts of the tree, you might be frustrated. Why didn't we put the 98 over there? Why didn't we put the right? It's fine. As long as we follow the rules of building a binary search tree, then this is the valid tree that we would have built. Of course, later on, you'll learn techniques to make the tree a little bit better looking, a little bit faster. But right now, we're just building a tree with no optimizations, no self-balancing, no anything like that. This is our binary search tree. Now, real fast, let's debug the tree. If we were to take all of the, all the numbers that we added and sort them, then that should be the numbers we see from left to right. This is another good argument for why we should draw the diagram in this way. Again, like same depth nodes. Let me just draw the depths real fast just to kind of illustrate the point a little bit. Same depth nodes should be on the same y coordinate or the same horizontal plane. Notice how 73 is the root node, and then 12 with 98 have a depth of 1, and then 10, 45, and 99 have a depth of 2, and then 11, 43, and 67 have a depth of 3, and then 32 has a depth of 4. So the deepest node we can find has a depth of 4. That's the 32 node, which means the height of the tree. Height is 4. Sorry, 5. The height is always the deepest node's depth plus 1, or the number of nodes you would have to touch as you found your way down to the deepest node. For example, if we wanted to get to that 32, we would touch 1, 2, 3, 4, 5 nodes. So the height of this tree is 5. Okay, let's debug the order of our numbers, because this is kind of easy to get wrong. So from left to right, we should see a sorted list. So let me just do little markings here to indicate that I'm seeing increasing or at least non-decreasing numbers. If our tree supported duplicates, then it would be non-decreasing, but since we don't allow duplicates, it should be increasing or an ascending list. So I'm going to do the 10. And as we look towards the right, we should see increasing numbers. So we got the 10 there, and then we got the 11 there, and then we got the 12 there, 32, 43, 45, 67. So far, so good. It's all increasing. 73 increases, 98 increases, and 99 increases. So from left to right, it was basically a sorted list, which is what we want. So we've created a valid ordering for the tree. Now maybe just think about all the rules of a binary search tree to make sure we did that right too. So is this a graph? Yeah. Is it a connected graph? Yeah. Is it a tree? No cycles in the graph? Yeah. Is it a rooted tree? Yeah. The 73 root node is the common ancestor of all other nodes. We have one node that's common to the whole tree in terms of ancestry. Does any node have more than 2 children? No. None of the nodes have more than 2 children. They've all got 0 or 1 or 2 children. And then the numbers are in order, and therefore this is a valid binary search tree. So in other videos, I'm going to talk about the time complexity and like, how fast it is to do certain operations or how imbalanced a tree may be and how that might affect things. But just so you know, this is not a perfect binary search tree. You can tell because it's a little lopsided. We calculated the height as 5. And let's see, where the heck is that calculator? I thought I had a calculator on here. Oh no. Oh, there it is. If we calculated the height as 5, you could probably imagine, and we'll talk about searching in a future video, like how do you search in a way that makes the tree super, super fast? Well, we certainly built the tree in a way that makes it super, super fast. We just have to get to searching later. But if we search properly through a properly built binary search tree, then at most, it should only take us height number of examinations to find our way to any piece of data or to determine that a piece of data doesn't exist. For example, I could say that the time complexity is O, and we'll do this in other videos, of H. It's always O of H, no matter what the tree looks like, no matter how lopsided it is. And what is H here? 5. That just basically is saying, in the worst case scenario, I would have to touch 5 nodes to reach the very bottom of the tree and determine that a value didn't exist, or find a value at the very bottom of the tree. So the worst case scenario, touch 5 nodes. So it's O of H. If we plug this into a calculator, a perfect binary search tree should be log base 2. So if we did log base 2 of n, where n is the number of nodes, how many nodes do we have? Oh, shoot. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, I think. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah. Log base 2 of 10. Notice how the number here says, well, it should take like somewhat close to 3 examinations, at most 4 examinations, but we just said it's going to take up to 5 examinations. So notice how there's a little bit of a divergence between the real speed of the tree. It might take up to 5 examinations, and log base 2, which would be a perfect binary search tree. So the more lopsided a tree gets, the slower it actually becomes. And we'll deal with that in future videos. We'll learn how to like detect that and balance that and so forth. But so we've built a binary search tree. It's definitely valid, if not, like super, super fast. And I think that's the end of this video. Thank you so much for watching. I hope you learned a little bit of stuff and had a little bit of fun. In the next video, I think I'm just going to build another tree for you so we can get a second practice in. Okay, future videos also are going to include searching and deleting nodes and modifying existing nodes and just a whole bunch of other stuff. Then eventually we'll do self-balancing trees. See you later. Hey everybody. Thanks for watching this video again. From the bottom of my heart, I really appreciate it. I do hope you did learn something and have some fun. If you could do me a small little favor, could you please subscribe and follow this channel or these videos or whatever it is you do on the current social media website that you're looking at right now. It would really mean the world to me, and it'll help make more videos and grow this community. So we'll be able to do more videos, longer videos, better videos, or just I'll be able to keep making videos in general. So please do me a kindness and subscribe. You know, sometimes I'm sleeping in the middle of the night and I just wake up because I know somebody subscribed or followed. It just wakes me up and I get filled with joy. That's exactly what happens every single time. So you could do it as a nice favor to me, or you could troll me if you want to just wake me up in the middle of the night. Just subscribe, and then I'll just wake up. I promise that's what will happen. Also, if you look at the middle of the screen right now, you should see a QR code which you can scan in order to go to the website, which I think is also named somewhere at the bottom of this video. And it'll take you to my main website where you can just kind of like see all the videos I published and the services and tutorials and things that I offer and all that good stuff. And if you have a suggestion for clarifications or errata or just future videos that you want to see, please leave a comment. Or if you just want to say, hey, what's up? What's going on? You know, just send me a comment, whatever. I also wake up for those in the middle of the night. I wake up in a cold sweat and I'm like, it would really mean the world to me. I would really appreciate it. So again, thank you so much for watching this video, and enjoy the cool music as I fade into the darkness which is coming for us all. Hey there. Let's talk about, hello there. Hello there. Let's build a binary search tree by just inserting a bunch of numbers, and we'll follow the rules.